for making it the last day. So we're happy to have Kontaro Ohmori, who's going to tell us about chiral edge states emerging on anion nets. Take it away.
Okay, thanks Justin for introducing me, and I supposedly a part of organizer, but I did nothing in it. So I'd like to thank Yuya in particular to making this fantastic workshop. In real, and today I talk about some lattice simulation, lattice model, and its numerical simulation. This talk is based on this collaboration with the Atsushi Ueda and Kanzei Inamura. Both of them were students at the second ISSP in Kashiwa. Now that they are now fresh postdoc at each, Ueda is in Ghent and Kanzei Inamura is in Oxford. Okay, so introduction. So the problem in this talk is to realize, I don't claim that I solve this completely, but I propose a direction for the solution to realize 2+1D chiral topological order on lattice. So, so the topological order is a gapped phase, and chiral in a non-trivial gapped phase, and chiral topological order is the ones with the chiral edge modes. If the system has a boundary, then on its boundary, this chiral edge mode has its characteristic chiral edge modes, which is gapless on the boundary, but the bulk is gapped. Okay, and the famous or most important example is, of course, the fractional Hall states. And for the high energy physicist or QFT person, if it's familiar as the IR gapped phase is described by the 2+1D Chern-Simons theory. So that's also a familiar subject. And so I'd like to realize that order on lattice in some theoretical lattice model. But there's it's a bit tricky. So it's not easy. And one thing is some no-go theorem about, like, it's not particularly about it's not exactly about the chiral edge mode, but it's very indicative that there's kind of no-go that there's no commuting projector Hamiltonian that realizes the chiral topological order by Kapustin-Fikovsky. So that's in contrast to the non-chiral topological order, that the non-trivial gapped phase without chiral edge mode. And for those topological orders, there's a famous Levy-Weyl model, which is a commuting projector Hamiltonian model that realize the any given non-chiral topological order. So, but the chiral topological order is harder, and it's even harder if we want to realize the so-called non-abelian chiral topological order. I will explain about the, well, basically when it's described by non-abelian Chern-Simons theory. And yeah, so we propose an approach based on generalized symmetry to realize such order on lattice. Yes. Well, I think in even when we talk about the non-factorized case, but we usually assume that that can be embeddable to the tensor product Hilbert space with a via the like local commuting projector. So yeah, the anion chain is in that case. So that's still, yeah. Okay, and okay, so the point, yeah, this approach is coming from regarding this anyons. So the topological order contains anyons, which is a quasi-particle with its characteristic fractional statistics. And now that's been known for a while. But now we can understand the anyons, even the non-abelian ones, as like spontaneous symmetry breaking of the non-invertible one-hot symmetry. So this data of anyons, I will explain later in more detail, is formed as a like modular tensor category, which is some mathematical construct. Okay, and in the long range, as I said, the topological order is described by Chern-Simons theory typically, or some topological QFT, and then the wall lines of anyons are regarded as the topological line operators. So then in deep infrared, there's an emergent one-form symmetry, which is a wall line of anyons. Okay, and then those anyons are also visible particle in the IR. So that means that this emergent one-form symmetry is also spontaneously broken. Okay, so that's the a modern understanding of this anion. So when the 2+1D system is in the topological order, then in deep IR it has a one-form symmetry. In general, non-inverted one-form symmetry described by the modular tensor category, and that's spontaneously broken. And so yeah, so that's so in this talk I'm regarding this modular tensor category containing the anion data as a non-invertible one-form symmetry. That's in general emergent in the IR. But just to realize the topological order, not imitate any real material, but here like just to realize the chiral topological order, we instead can impose exact one-form symmetry. That's one lattice, and then if the dynamic is so that it's gapped, then we can say that the gapped phase should contain anion of C. There can be additional anions, but it should contain it. The anions corresponds to the MTC that impose in the microscopically. Okay. So the hope is to construct some model that has the exact one-form symmetry, the modular tensor category symmetry, and if we want it to be chiral, it should break the time reversal symmetry. So also find a Hamiltonian that preserves the chiral symmetry and preserves this modular tensor category symmetry, non-inverted one-form symmetry, but breaks the time reversal symmetry. Okay, and yeah, so that's the strategy, and yeah, and that can be achieved by the 2+ version of anion chain. So that's the anion chain is first introduced. This 1+1 version of anion chain. The original one is first introduced by the Microsoft Q people, and then also like extensively generalized to like the general fusion category case in the by Arsene Fendry-Mon, as Yamaguchi-san talked to us yesterday. Okay, and okay, so the model we found we created is not at all solvable. Analytically, so we did a numerical method, and we did find a chiral edge mode in some parameter space of the Hamiltonian. So this is a teaser just to show. This is we have some model on lattice. This is open rectangular lattice, and This is a heat map of local Hamiltonian expectation value for the difference for that for the second order excited state and the ground state. And we have a one parameter family of Hamiltonian. So this is a different parameters. And here is like non-chiral. There's no it's not some bulk excitation, but here and here we see that the second order excitation is concentrates on edge, and there's also like way to measure the approximate momenta, and that's like going one way or the other way depending on the parameter. I will explain it better in the talk. So any questions so far about strategy? Great.
So you perform numerical calculations for, I suppose you have an infinite family of models, is that right?
Oh yeah, so I have one parameter family of models, and yeah.
But there are infinitely many modular tensor categories.
Oh yeah, we pick particular one.
Yeah. So okay, so you pick a particular one.
Yeah. Of course, I can do finitely many simulations. Yes. So yes.
Right. But okay, you could have chosen two, but okay, you chose one.
Yeah, I just picked two cases. Yeah, two modular tensor categories.
Okay.
Yes.
The chiral edge state is lived in 2 plus 1 or edge of 2 plus 1.
Sorry.
The space living chiral edge mode is 2 plus 1 dimension or edge of 2 plus 1 dimension.
Edge of 2 plus 1 dimensions.
So 1 plus 1 dimension.
Yes.
Thank you.
Yeah, that's like I have rectangular lattice, and this excitation was almost lives in this region. Okay. So I've done introduction, then I will give the review about the anyons in the modular tensor category, and then I will explain our work. Okay. So anyon, like as I said, anyon is a causal particle with fractional statistics in 2 plus 1D topological order, and it's understood as a topological line operator in the IR fixed point QFT. Okay, and so in microscopically we can define the anyon type that as like quasi particles that cannot be like two excitations are in different anyon types if you cannot adiabatically change one state to the other via like local adiabatic evolution. So that's a rough definition. And the anyons carry some universal properties. For example, one important property is the topological spin. So that's a spin, basically, of anyon, and that can take any rational value, as opposed to the boson fermion, and that's why it's called anyon. It can have any spin. It also have a fusion rule, so you can collide to quasi particles. And so so we assume that each of them cannot be converted to like other anyon types by definition. But if you put the two things close to each other into the adiabatic deformation, the local one, then you get the different excitation in a different anyon type. So that's defines fusion. Okay, so it just basically collides two quasi particles, and yeah, so that's usually written with this symbol. you fuse anion A and B, and you get the C. But you might get many types of C. So in general, this is a sum. Yeah, and the coefficient here is integer, is called the fusion coefficient, and that's basically counts the number of ways to adiabatically fuse from A, B to like C. Yes.
You said you have in your lattice model there is a modular tensor category symmetry.
Yes.
So that means that it doesn't have anyons. So I don't understand what do you mean, your terminology. If there is symmetry, then there are no anyons.
So the particles, yeah, there is a dispute about whether there is a finite energy.
Right.
Yeah.
Right.
So one way of one thing is that you can slightly break the symmetry, and then there's a like definitely finite energy. Well, in numerical simulation, I do have symmetry. Well, yeah. I think okay. I didn't. So for purely technical reasons, I couldn't study the bulk perspective. So I can say, but I do. Yeah. Yeah. One excuse is that still you can in principle easily add a term that breaks a one-home symmetry, and you do. I do expect that phase is the same with very small, tiny deformation, and then still. Yeah. I don't know. Yeah. Well, but it's chiral, so it's definitely chiral. So it's very hard to come up with the interaction breaking it. Okay. So. Okay. Oh, I didn't. Yeah. So and the also there's a braiding. So if you have two anyons and then you move like rotating in 360 degree, and you get not in general phase, you get some action, and that's called the braiding action. So that's also, yeah, so that's called braiding. So these are a part of properties of anyons, not even, yeah, this is not a full list, but the part of properties, and those properties are nicely packaged in terms of the modular tensor category. So I did not really explain what the modular tensor category is, but that's some mathematical construction contains the information, the universal information about anyons. Yeah. And yeah, so and one property that's important in this talk is quantum dimension. So so for anyon type A, that's kind of you should regard it as like the number of internal degrees of freedom of anyon. Yeah, but I put it in the code because it is not in integer in general. And yeah, so to define it, you put anyons in like n of the anyons at the same time, so separated with each other, and then supposed to count this lowest energy states in an in infinite space and separated each other in the limit that the distance also goes to infinity. So in that, then in general there's a like lowest energy degeneracy in the lowest energy states in such subspace, and that's that dimension of that degeneracy goes like asymptotes to like power of some number. So that's a property expected for topological order, and this exponent is called number of internal degrees of freedom. Okay? So if you're instead thinking about just just a spin of like in a trivial phase, and just you put n of spins, then you get the 2 to the n vector space. So that's about that. Okay. Yeah. So this quantum dimension is in general non-integer. So it's described. Yeah. So in general, this vector space is not local. It's not manifestly local. Yeah. And when there's some anion that contains a quantum dimension greater than 1, then the topological order is called non-abelian. Oh, this is not true. But this is some definition, but this is not. Well, sorry, I'm right. This is fine. So I'm confused. Yeah, this is fine, and yeah, it's called non-abelian, and the topological. Oh yeah, I wrote the same sentence twice. Sorry. Yes. Yes. Maybe he's.
So what do you mean by AN sector on Rn?
Oh yeah, so you put this is you put the anions, and n of them, and sorry, R2. So,
R2,
so,
okay.
so it's confusing. This is sorry about that. Okay. Because the examples of anions and modular tensor categories are like so for like this. So abelian anions, which is for only dimension 1 anions, and famous one is U1 level K. That's basically describes the fraction Hall state, and the fusion law, that the rule that how the anions collide is forms just a zk. Okay, and other important example is a toric code. That's the IR is described by the topological Z2 gauge theory, and these are like forms. It contains the four anions and it's Z2 square fusion law. The non-abelian ones, there are two famous examples. One is called Ising MTC, and the other is Fibonacci MTCs. Okay, yeah, and other examples are like the anions for the topological line operators in the Chern-Simons theory for non-abelian gauge group. But here I'd like to focus on this Fibonacci case. So Fibonacci in a Fibonacci MTC or Fibonacci topological order, there's a one non-trivial anion type. So this one is a trivial anion type, so that means there's nothing. But this tau is a non-trivial quasi-particle, which fuses to either itself or nothing. And the quantum dimension is golden ratio. So, and the topological order is called chiral if it does not meet a gapped boundary condition. Okay, so the boundary so for if you have a such system, then you do have gapless mode. That's called a chiral edge mode. And one diagnosis commonly used to know that whether a given topological order is chiral or not is the chiral central charge. And there's a formula for the chiral central charge in terms of the anions, so it's easy to compute from the MTC. There's some formula, and when this number is non-zero mod 8, it's chiral. So that's a theorem. The converse is not true, and we wrote a paper about that. But but here it's enough to say this direction. And yeah, so the chiral ones in the previous examples are like fractional whole state and the Ising MTC and the Fibonacci MTC are chiral, and topological order is not chiral. So that's yeah. And one particular non-chiral topological order that's important in this talk is doubled topological order. So given any MTC that you can define its time reversal MTC. So just in a sense, just taking the inverse for the braiding matrix, and okay, and so for any on type in MTC, and we assign, so in the time reversal we assign some complex conjugate with the opposite spin. Okay, and then the chiral central charge from the previous slide is negative. So then we can just stack the two systems, okay, in two phases, and that's like just cancel the central charge just cancels out. So it central charge is 0, and indeed it's for any C that C times C bar is non-chiral. So there's a gapped boundary condition. There's a theorem. Yeah. Okay, and it's also like as a terminology, yeah, it's also obvious time reversal symmetry exchanging the C and C bar. Okay. So any questions so far?
In general, what is the relation between time reversal breaking and the chiral versus non-chiralness? So if it's a chiral, then it must break time reversal, right?
Yeah.
But if it's non-chiral, then it can either break time reversal or preserve time reversal, right?
It can definitely preserve the anomalous time reversal. It's I'm not sure.
So
It's
it's not like a 1-to-1.
It's probably not 1-to-1 state, but there's anomaly. So.
Oh yeah.
Okay, so then I move on to my thing. Okay, so let me start from the easiest model, which is story code, and it already appeared several times in this conference. That's a computing project Hamiltonian on lattice, and each edge we have spin. And and Hamiltonian is a sum of like a term and B term. A term is associated to a vertex, and it's a product of X on like spins adjacent to our given vertex. And B is a product of Z of power Z matrices that for the spins contained in the bracket, right? And model. And these AB and BP commutes with each other, and also commutes among themselves, obviously. So the ground state for this model is given by the state that satisfies this condition, that for any eigenstate for any A or B operator is 1. Okay, and so that's the ground state. If you violate this condition at some vertex, and that's also a energy eigenstate, And that's E. That creates a E anion. Sorry. Yes, C E anion at V. And if BP has a negative eigenvalue, then it has an M anion. Okay. And so in the IR, there's a E to generating anions. There are a third one, F, that's a marginal bound state of E and M. So that's a Z2 times Z2 emergent ones. Okay. And yeah, so that's a very basic Lux model. And then there's a Levin-Weyl model, which is a vast generalization of toric code. And so it's still a commuting project Hamiltonian for the non-chiral topological order. And yeah, and the C box times, so C times C bar is also non-chiral. So for any MTC that it's double is realizable in particular. And it's a vast generalization of toric code. On edge, we put the vector space, the Hilbert space whose dimension is the same as like number of anion types, and there's also each vertex is also there. In general, there has to be degrees of freedom, and I don't describe the term, but Hamiltonian still looks like A term and B term, and like for each vertex and for each bracket and commits with each other. Okay, so and yeah, so this is a exactly solvable model, and that means a gap boundary condition. Okay, so that's a Levin-Weyl model, and the model of construction. So I'm explaining some rather like trying to provide a physical motivation of our model. So our model can be understood as some model of like Levin-Weyl model, but filled with anions. Okay, so we start from the Levin-Weyl model for the double, and pick an anion type. That's arbitrary choice, and the place copies of them on lattice. So this is not exactly what we did, but morally speaking, what we did. So we place the anion in as a lattice to form, in this case, rectangular lattice. And yeah, and as I said, if this row is non-abelian, and there's a like internal state, so the vector space, this lowest energy state for this array of anion is non-trivial. This is more than one-dimensional vector space. So it is a like internal degrees of freedom in the array of anions. Okay, actually doing it, so finding in sector like anion sector in Levin model and doing something is hard. So it's in practice we used the 2+1 version of anion chain. So there's some systematic way of constructing this space, or something like that space, and then we used it. And in this formalism, the non-inverted one symmetry is manifestly realized. So there's So I can explain the detail, but there's a way to construct this space, the space of internal degrees of freedom of anions in this way. But still, at this point, it's just the degenerate eigenstate in the non-chiral topological order. Then we put additional Hamiltonian on top of the Levin one. That's lift the degeneracy in this sector. Okay. So in this sense, it's a kind of anyon version of Heisenberg model. So we put instead of putting a spin, we put anyons, and these anyons doesn't move, but the internal degrees of freedom have interactions. Okay, and this we picked this particular interaction that brace. So using an anyon chain technique, we can easily find this operator that moves this anyon to that. So we pick one bracket in this anyon lattice and braid, like rotates this 4 anyons to so this is a additional bracket action. And there's no very good reason to pick this one. This is kind of random choice, but obviously breaks the time reversal symmetry. Okay, and we do have a one parameter here because this is now non-Hermitian operator. So we take the complex conjugate, but we can put the phase in front of it, and that's a parameter. And it's also like from the linear chain technique, it's manifest that this interaction preserves the MTC symmetry. Okay, so the model, the symmetry structure of model is just this and breaks the other MTC symmetry, but because we are putting this anyon row, and also like breaks the time reversal symmetry. And as I said, the C symmetry, the Neuberger one symmetry ensures that if the system is gapped, then it should contain anyons in the sense maybe so as Zoha has pointed out that the ones corresponds to C might have infinitely heavy, but I also contain it as anyons, and this is, in other words, the MTC symmetry, because it's a modularity, is free anomalous, and there's no way to shrink it. So what we expect is that with the generic parameter, general parameter, there are places that this Levin phase goes to something else, but the C part should be preserved, and the C bar can be replaced by something else. Okay, and this emergent one is if this emergent one is not the C bar, then it's chiral. Then it's possible that it's chiral. Okay, but it's also possible that this C emergent is C by itself. C by is emergent again, and then it's not chiral. That's also a possible scenario. Okay, so we hope that with some parameter choice, it's chiral by lifting C bar and replacing something else. Okay, so and the model is not exactly solvable, so we do numerical simulation. Any questions so far?
So you said that you put the anyons like the lattice, lattice shape, but then it means that you constrain a possible state of the model, or it's a property of the Hamiltonian itself.
So one way of thinking about our model is just it's like one sector in the Levin band, and then So that's a huge degeneracy in higher energy states. There's a huge degeneracy, and then we did we consider that huge degeneracy and other additional Hamiltonian, so that this degeneracy is broken. Yeah.
So with your new Hamiltonian, that configuration of anyons are automatically.
Yeah, so the way we formulate
realized.
but the way we actually formulate on computer, then yeah, this presence of anion is an input. Yeah, yes, yeah, yes. Yeah. Okay, so I talk about the numerical summation. So we did, as Okuda-san pointed out, we cannot do infinitely many possible MTC at once. So we just pick the small ones. Small MTCs, those are like Ising and Fibonacci. And in this talk, I concentrate on the Fibonacci case. Okay, and the methods for numerical simulation is a MPS-based density matrix renormalization group. MPS is matrix product state. And so that's a sophisticated variational method. And okay, and so this is 2+1D system. And we regard it as a 1+1D system with long range interaction. So just we have yeah, I should have a figure, but like it's a 2+1D system, and we regard this as a 1+1D system in this way. So yeah. But then there's a long range interaction if you unwind this to this space. So I guess I have a time, so maybe I can do expression. So if I label the lattice like this, then we regard this as like 1, 2, 3, 4, 5, 6, 7, blah blah blah, and in 1D, and then like so there's a bracket action. So there's a bracket here, and in this 1D way of observing it, it's like 1, 4, 2, 5. So it's like this one. So like this. That's yeah. So this method is only suitable when one length of one side is small. If it's a so it's we do the rectangular lattice the yeah n by n. So that's a way. Of course, it's more desirable to develop the more genuinely 2+1D algorithm, but that's on yeah. What we could is this and yeah, and so I think to the audiences, it's still obscure what we did in the actual computer, and because I talked about some abstract MTCs and blah blah and like anyons, variance grading, but that's not obvious to how to convert it to a number in a computer. But the good news is that you don't actually have to know. There's a package, and the really nice package that's surprisingly that allows you to directly talk in terms of MTC. So you just specify that I'm talking about the Fibonacci, and then like I braid this anion in this way, and it computes. Okay, so it's very nice. It's I don't know why these guys in again created that, but I really appreciate it. It's yeah, it's mind blowing, and yeah. So that does that. So we just use these packages and yeah, and I showed the results. So yeah, this is the figure. This is basically the eye-catching figure. So this is a result for Fibonacci, and the width is 6, and height is 12. And this is finite. This is a finite DMRG, so it's a finite system. And yeah, this is a heat map of expectation value, energy expectation value for the and difference of it for the second excitation, second excitation of the model and the ground state. Okay, and so there's a parameter theta in the Hamiltonian. There's like some 3 different values. And also like there's a small arrow if you can see it. So that's a phase of expectation value of this local rotation. So it's more speaking some angular momentum, and that angular momentum is like this. So on aggregate, there's a flow in this way in this parameter. And in this parameter, it is going the other way around. So this is some promising result, and I show you. But this is rather eye-catching, and I show you more robust thing. So the more robust thing we did so-called infinite DMRG. There's a way to, I don't explain, but there's a way to do like a DMRG for like one side is infinite. So this is infinitely long chain. This is 6. Sorry, and it should be 5. So 5 times infinity. And yeah, so this is a correlation length. The chi is a bond dimension. If you don't know it, this is some cutoff to do the numerical computation. Okay, so this is I have finite source, so there's artificial cutoff, and then so depending on the cutoff, there's a correlation length. So we expect that the xi of infinity is the actual correlation length. Okay, and this figure like these gray dots are like for smaller chi, and the black dots are the larger chi, and correlation length. So if it's okay, so if there's a gapless mode, the chiral edge mode, then this strip is on total gapless. The bulk yeah. And if that happens, then correlation length should diverge. So if we increase this chi, then this correlation length should go up forever. So the x-axis is a parameter. Okay, and here it's like that. So if we increase chi, then correlation length goes up. Here it's not. It's like we increase the chi, but correlation length stays here. So it's more like a gapped phase. Okay. I'm talking about gapless versus gapped on the edge. Okay. Well, I really do not know whether this bulk is gapped, but I'm assuming it. I will. Well, yeah. And so there are 2 promising parameters here and there. I think this is type of one is 0.1 and the other is 0.9. So and then we also compute for those parameters the entanglement entropy for the subregion A. So the region A is just a half phase from some point. So that can also be easily be computed in the DMRG. And the plot of that entanglement entropy versus the correlation length. So the correlation length sets artificially the length of the system. So And that's and then we can read off this central charge from this entanglement entropy. And for this point, it looks like it's on linear line, and the central charge is by angle of this line, and that's 0.7, and this thing is like 0.8. Okay, so we think that here we have C equals to 0.8 gapless mode here, and here which way? Sorry. Yeah, here it's 0.8 and this is 0.7. Okay. And we can also like study the entanglement spectrum. So that's so entanglement entropy is entropy for the reduced density matrix, and entanglement spectrum is just a spectrum for the reduced density matrix, and it's expected that we should get the spectrum is a spectrum should coincide with the eigenstates for the spectrum for the boundary conformal field theory. So that's basically like count the BCFT lives here. Okay. And yeah. And what we saw, so B is a 0.1 and this one is this. So we saw that the spectrum that the lower line states are like coincide with, well, for this case, it's a tricritical Ising model. This is with a particular boundary condition. And here it's a 3-state pot model on a particular boundary condition. Yeah. So this dots are numerical value. The cross are theoretical value if you assume that there is a chiral edge mode corresponding to tricritical Ising and 3-state. Yes, so we have this configuration. So if we have chiral edge mode, we have left mover here, right mover here. So on total, we get the usual CFT, one CFT, not double. Oh yes, I will comment. Yeah. So yes, C minus is not the same. I agree. So we expect that. So it's okay that in the bulk there's additional emergent Van symmetry. So that's, but still like it's totally consistent that these chiral edge modes with the bulk of this kind of anyons contains Fibonacci as a tensor factor, and times this is a anyons for the spin group transformer theory, and the 3-state posits. Yeah. So those parameters we expect that the bulk phases are those. Yeah, and there are parameter space in where we did not see any like chiral edge mode, and that should be like non-chiral space. Okay, so these factors are not in the exact microscopic model as an exact symmetry. So these two should be emergent, while these are imposed microscopic. Okay.
It sounds like they don't control over it. So maybe if you do better simulations, you find out that it's not the way.
I agree. Yeah, I agree. Yep. I mean, if you want the to create a particular, yes, I agree. So yes, so I presented a model with a exact non-invertible one symmetry, and so that's can be understood as a like putting a lattice of anyons in the linear model, and that's using the anion chain technique, we can construct the symmetric, the non-invertible symmetric Hamiltonian, and still breaking time reversal symmetry. And then the symmetry structure features the assuming gapness in the bulk. The C times C bar anyons in the Levin-1 is replaced by some C times something else. Okay, and did the numerical simulation, and we have some evidence that looks like this bulk phase. And yeah, so certainly there are several or many weak points. And one weak point is that we didn't do any bulk. We didn't directly compute any bulk property for the many technical reasons. So we only did our open simulation on the open chain or open lattice. So when there's a chiral edge mode, then there's a like chiral edge mode. It's very hard to detect the bulk property directly, like finding actually the bulk anyons, emergent anyons, and even just checking that bulk is gapped is not so easy because the boundary is gapless. So see. So yeah, so that's a weak point and to improve. But still, yeah, one can play with other MTCs, just replacing the MTC to another, and it's fine. And yes. Oh, and I should, well, anyway, yeah, and at the technical point, of course, yeah, we did the DMRG, but it's better to do the 2+1D method. That's called the PEPS, and yeah. But the point I want to emphasize here is that the anion-based model is a vast generalization of conventional lattice model where you put the factorized tensor factors here is vector space, and it's still local model, and thanks to these packages, it's actually like kind of easy to play with. So that's my main message. And that's like in the same spirit that the Hayato-san and Hidaka-san proposed. So they proposed to simulate the Young mills, to perform Young mills, and by deforming a living event. We try to replace this by something else, but they rather put like lift both by the diagonal lifting, and so that's in terms of Chern-Simons series, G level K times G level minus K, and put some bifundamental and lifts to the trivial phase, but in between there's a Young mills. So that's and their formulation is also like on the same like anion type formulation. So that's in the same spirit. So that's the end of my talk. Thank you for listening.
Thank you very much. Are there any questions?
Could you go back to several previous? And so I'd like to know how do you understand that emergent spin 7, spin 3, for example, from looking at spectrum in more detail?
Oh, so this, okay, so yeah, there is a correspondence between this chiral edge mode and the bulk anyons, and that's that's like this particular MTC should be should be like a category of representations in this chiral algebra realizing tricritical Ising model. So yes.
In your previous figure, so for example, can we identify which one is, for example, spin or which one is energy counterpart?
Oh, you're asking us the spin of the
Yes, spin. So critical
Yeah.
Ising has several spin operator and several energy.
Oh yeah, so yeah, so yeah, we can detect these two modules in this critical case either way. So this tau corresponds to the also the input anion in the microscopic model, and yeah, so that's so this MPS is like symmetry preserving MPS, and when we do this form the entanglement spectrum, there's a two channels in the reduced density matrix. So we are using the formalism that this symmetry resolved entanglement spectrum is automatically achieved, and so then there's a two symmetry sectors. One is trivial and the other is tau anion, and this shows the two different modules for the tricritical Ising.
Any other questions?
Okay, so the values 0.1 pi and 0.9 pi for theta of theta are not particularly special, right?
Not particularly special. That's just a numerically promising point.
Yeah. So you showed us a figure where the horizontal axis, yes. So the theta over pi is in the horizontal axis, and
So the 0.1 is here and 0.9 is here.
How are we supposed to understand this? Is there are there supposed to be phase transitions in the?
So yeah, I do not know in detail. I know really nothing about this, but the probably yes. So this thing looks this point looks like non-chiral. So there should be somewhere like phase transition here, but I really don't know any detail. I do need a more better technique so to say.
But you expecting or assuming
I expect that here that this is some other bulk phase even. So this should be some kind of around here or this point. There's a chiral topological order, and then this is not non-chiral, so there should be some phase transition in the bulk.
Okay, thank you.
Any other questions?
Oh, yes. I'm a little bit confused. You have some definite Hamiltonian in 2+1 system, and but you also imposes the some particular categorical symmetry. That Fibonacci one. But how those two are related? So you pick up some subsector in the or Hilbert space or something like that. That is what you are doing.
So that's if you embed the model in the Levin-Wen, then it's like the Levin-Wen has Levin-Wen also has this MTC symmetry, and this is we pick some high energy degenerate state, and then deform project onto that subspace, and then add Hamiltonian without breaking the symmetry.
I see. So you are seeing this something in the very subsector of the
if we embed it in the Levin-Wen.
Oh, I see. And you said that picking up the some subsector can be do numerically.
Yes,
By using that
Yes,
code
yes,
also.
yes.
Thank you.
Any other questions? Okay, if not, let's thank the speaker again.